Okay, we are talking about the fourth central moment in today's lecture. I bet you guys can guess it. We're just going to take our centering formula here and raise it now to the fourth power and take the expectation of that. So, again from last time, we had 5 2s, 2 1s, 3 5s in our value set. The differences between our observations and essentially our average were as follows: negative 1.7. We'll raise that to the fourth power. So nothing has changed here. Multiplying that by 0.2. And then we're adding negative 0.7 raised to the fourth power, multiplying by 0.5. And then we're adding 2.3, raising to the fourth power, and multiplying by 0.3. So nothing's really changed from anything we've been doing thus far, other than we just keep changing the exponents. That's the big takeaway, at least in terms of the math here, to get us started. This is actually going to equal approximately 10.19. And what this is essentially telling us is it's basically just saying how our variability is distributed. So it's not a measure of variation, because you could have the same variance and the same mean with two different data sets, but you could end up in a situation like this where, in fact, our variability is differently distributed. And what that means is that you have... It means that you have extreme observations occurring more frequently. So things on the tails are occurring more frequently, and that would be considered high. Where we're going with this is we're going to say it's high kurtosis. Now this is just the fourth central moment, just like skewness, and I'm going to abbreviate kurtosis as Kurt. We have to take the fourth central moment, but it's not the entirety of the equation for kurtosis. And so just like with skewness, we're dividing by sigma, this time to the fourth power. So your sigma is still associated, your sigma's power is still associated with the power of the central moment. In this case, both are to the fourth power. So then recall we had sigma squared equal 2.41. If we want sigma to the fourth power, we're going to have to raise both sides again, squaring them. So because we already have sigma squared, we raise that to the second power, so 2.41 to the second power. That's going to give us 5.8 approximately. There's a little extra in there, just like 10.19, so we're kind of rounding here. But with 5.8, that gives us our sigma to the fourth power, so that's equal sigma fourth power. So then we literally just divide these by one another. So 10.19 divided by 5.8. I'm going to erase this, make some room for us. And that's going to equal, again, approximately, I'm rounding again, 1.76. So now we need to know what this actual value is telling us. And then I want to give you guys a few graphical representations of what high and low kurtosis looks like. So kurtosis, we're going to use Kurt equals 3, so kurtosis equals 3, as a benchmark for us. That is the normal distribution. So it's a benchmark we should be familiar with. So that will be our point of comparison. Then if we have a kurtosis that's larger than 3, we say that's high. So that's high kurtosis. If we have a kurtosis that's less than 3, we would consider that a low kurtosis. So in our case, when we calculated 1.76, our data set was actually low kurtosis, lower than normal distribution. Now what a high kurtosis looks like, suppose we have normal distribution, and I'm going to draw 2 of these out in black. Then in blue will represent our high kurtosis. It can look really one of two ways. and forgive me, my curves are kind of terrible, but it could be the case where the blue on the tails, it has fat tails, it's over the black. That is, high kurtosis has higher tails than a normal distribution, and it'll be underneath the black for the entirety of its crossover. So when it crosses over from the left, it remains under the normal distribution, and then it will remain so until it crosses over the right, and then its tails will be higher then. So for the entirety of it. There also could be a case where, again, you would have a fat tail, but you kiss the top of the normal distribution curve. So they have the same value at the top, they have higher values in the tails, and then in between the center and the tails, it will still be lower. The key here, though, the key takeaway for a high kurtosis that I want you guys to remember is literally just the tails. It's literally saying we have more frequency in our extreme values in terms of our distribution. So more of our values are on the extremes in the distribution than they are relative to, say, a normal distribution. So that's the big punchline for high kurtosis. And then again, we'll just draw a couple of low kurtosis examples here. So we have a normal distribution like such, and then I really should draw these with a little more space, but we end up under, and then over, and then under again. So we're over in the center now, and then we're under on the tails. And that's the big key. The tails are the key. Doesn't really matter what's happening as much in the center, because you could imagine a weird scenario where you're under, and then you're under, and then you're over. Sorry, my drawing skills are... And then you kiss, and you're over, then you're under. So you could imagine a scenario where we sort of flange out in this weird middle ground here. So we're above where I'm drawing these X's now. We're under on the tails. Again, that's the key for knowing whether or not we have low kurtosis, what it's really describing. But then we end up actually kissing the center again. So those are the big takeaways that I want you to grab off of this, understanding kurtosis, what's going on. With that being said, I will see you guys next time. That should wrap us up. So we'll call it there.